Okay, good day, ladies and gentlemen. Welcome to the Fusion 360 Generative Design webinar for Micrographics. So, as you can see, we've got our lovely Fusion 360. Just a bit of a thing in the background. You can actually see some of the generative designed objects in the background here. So firstly, a bit about the introduction. Hi, I'm Quinn Kennedy. I'm application engineer down here at Micrographics, Durban. Part-time, yes, trying to take over the world. Yep, my normal spiel. Cool thing over here, if you take a look actually at the clause of this, you'll see that's actually a generative designed element over there. I'll get to a bit as to why in a little bit later as to why they'd want that. So a bit about our agenda. Firstly, our intro, which I've just gone through. Then, very briefly, what is generative design? Places that are already using it today. How is it done in Fusion 360? And then we'll have an outro. Just included this. Did have this nice little graphic over here, which basically shows as to the way that you would want to think about how generative design works, and also a lot of 3D modeling. In this case, explore. So we can generate multiple different iterations of that model. Optimize. We can find the correct one that suits us for that job, which would be materials, stiffness, mass, or lightness. Then also we can then go for our validation. Check and make sure that when we simulate that it does exactly how, well, what we want, when we want. Okay, so what is generative design? Well, in a nutshell, it's a tool to create CAD-ready geometry given the set algorithm limits, or algorithms, limits, conditions, forces, and or geometry that's given. It actually bridges between human and machine design, and it actually creates the true meaning of the word CAD, which is computer-aided design, because at the end of the day, we are allowing the computer to aid us actually in the design. Because with most of our drawings to date, what we have done is we've told the computer, we've told it, you go from there to there, or we want this item going from here to the other position. And yes, we've been able to do things. We've been able to do also things like topology optimization or various things like that. But still, it required a lot more of the human interface. Now what we're doing is we're giving it set parameters, set limits, etc., and then we work at it from there. So as you can see over here at the bottom, I've actually got a little lamp that was generated. You can see the rendering here on the right. Quite a cool little one if you ask me. So a little bit about it. Maybe this would also explain it a bit better, because if we take a look at CAD, how it's progressed, or the way that things have actually progressed and how it's helped people or our designers out there. So firstly, in our top left over here, you can actually see we've got a 2D CAD drawing. So like 30 years ago, came in and this revolutionized the world. Not so in maybe like what people thought, like speed-wise, because arguably I've actually seen a lot of guys that can draw by hand faster than a lot of guys can draw in CAD. But where the difference came in is the ability to then modify it afterwards. Because literally, as the saying goes, you go back to the drawing board, you like start from scratch almost, and then you have to go from there. And then it also gave us a lot more control, size. We could easily keep a lot of drawings in a smaller place, etc. So anybody's worked in a drawing office, anybody's worked in a drawing office with lots of drawings will know that can be quite an interesting thing, keeping hundreds or thousands of drawings. Then the next thing that we went to on the top right over here was the 3D, which opened up a huge area for us in design, as well as being able to take a look at something and actually see, to portray how something will be in real life. Because a lot of people can understand a 3D image or a 3D model, but not a lot of people can exactly see a 2D and see the different views in it and then understand how it's coming together. With our 3D, we were able to now show people how things are coming together, show assemblies, how parts were fitting together, etc. You could then see, hey, is this going to work? Is this looking okay? and how is everything working in tandem. We then went from there to the next stage, which was then our simulation. We could then take our models, 3D models, put them into or through the simulation and then see, will this break? When will it break? How can I make it stronger, lighter, and better? Now, today, we've got generative design, and this is what you can see on the bottom right here. And as you can see, it's this bicycle frame, and it's showing these designs on it. And now you'll notice there is multiple different designs, and this is what I was talking about this iterations that it's giving you. It gives you multiple different solutions to the problems that you're giving it. And if you also look, it's very organic looking. Now, something that will be cropping up in a bit later is that you wouldn't even imagine these designs beforehand. It looks like actually nature itself crafted most of this, because nature is actually an amazing thing at modeling. So some places that are actually already using this technology today, which you'll notice is VW, Airbus, GM, JPL, Honda, just, a few of the smaller names out there. So if we take a look at things like, let's say, VW, how does VW use it? Well, in this case, they use it as a showcase to see what they could do. And this was actually a restoration of a 72 Volkswagen Kombi, which is quite interesting. And while playing around with it, the one engineer, or designer should I say in this case, found that they could decrease the weight of their wheels by 16% over traditional designs. Just remember, with things like the vehicles, especially in flight, which I'll get to with the Airbus one, any little savings you can do in mass, so your weight to the vehicle, it drastically decreases fuel consumption. Or maybe not even drastically, but it does decrease your fuel consumption quite a bit. So when we are talking about weight, you're also talking about not just also the fuel that you're saving, but also the environmental impacts. Also, which was quite interesting, is that it increased the production time. Or should I say decreased? Sorry, that was actually me being a bit of a blunt moment. Decreased the production time decreased it from 6 months down to 2 months. So that was also quite a nice mean feat. I mean, literally, they halved their production time. And if you take a look here at the Volkswagen, again, the mirror over there was quite interesting, but also take a look at the wheels. And as I said, this organic type look looks like Mother Nature crafted it herself. Next thing, GM. They had the seat brackets. Now, seat brackets, as you can imagine, if it's a seat bracket of a vehicle, it has to pass some pretty stringent requirements that those are the things keeping you alive. So if things go wrong, how do we keep the occupants safe in the vehicle? Well, through generative design, they took the original that they had, modeled it up, gave it some the parameters, the forces, etc., and they came up with over 150 design iterations. 150. Some so unique they were never even thought of before. These also came out to be a 40% mass saving while being 20% stronger. And if you take a look on the left, I know it is a bit out of focus at the moment, but if you take a look on the right, you can actually see that there's you can see the basic geometry looks similar, but the one on the right looks very organic, like it was grown. So this is how, an interesting case of how generative design can take something that's already pre-existing and improve upon it. Next we come to Honda with this crankshaft. And if you take a look at that crankshaft, it does look very strange. To me, it actually looked like it had melted and poured out and then solidified. But yeah, so in here, you've got it that they managed to streamline their prototyping and design and rework. So they could go and they could take their original ideas, their designs, they could feed it into Fusion, work around with it, test their designs, test their iterations, etc., and then get back into reworking the parts. Now, one thing I mentioned previously that is actually quite interesting about this is that well, I did mention it, which is it creates CAD-ready designs, meaning that you can go to it, whatever this spits out, which I'll show you a little bit later, it is actually, you can take it into as a solid model and then work with it further. So if you need to tweak a little bit, if you want to try something else with it, you can do that. Meaning that this is not just spitting out an editable mesh, which is very important because anybody that's worked with meshes before in Solid, you realize that it can become quite cumbersome, especially if you're not used to it or if you're not the best at working with it. And also what I like also about this over here is that you can actually see that they've used here different manufacturing processes. They've used a combination of additive to build it up, and then to make sure that they clean it up nicely, they use subtractive. So they put it through CNC or mill, and then they turn it to get the nice finishing that you now see on the system. So it works not just with one system, but with many different types. Now, even Tadaka, I really hope I'm pronouncing that right. I do apologize if I'm not. Himself said, he was one of the designers, by the way, who said, a configuration I had not even considered as a designer. And now this is something that comes up more and more and more. Every time you see this, is that people look at it and they're thinking, wow, this is amazing. I had not even thought of this because, like I said, we are letting the computer do the design work. We are basically becoming the ones that are just, instead of drawing the solution to the problem, we are giving the problem and we are analyzing to see, is this solve the problem? And as you can see, they got a 50% weight reduction, which is massive if you consider it. Like I said, prior, these guys would only be getting small percentages. Now we're giving them 50% of a weight reduction in this case. Next thing is Airbus, and this is a partition. As you can see, I don't really have much text on this because the visuals speak for themselves if you ask me. Now, in the bottom right here, you can actually see that they've got these partitions. Well, a partition. So the partition is over there at the back. And if you take a look over here, this is the existing partition here on the left. The existing partition came in at a weight of 65 kgs. And then with the tests, they've found that it was having a displacement of 108 millimeters. So if you take a look here, this is something I just want to point out. You'll notice that when the force was applied and a simulation was run, you can see they've got this really like cherry red hotspot, and it then very quickly kind of fades through the different magnitudes all the way up until you get the light blue, which is touching the edge barely, and then these outer edges aren't really under load. So it does spread out evenly over the area, but it's very concentrated over here. Whereas if you take a look at what they call the bionic partition, you can actually see that, number one, take a look at their weight. 35 kgs. 35 kgs versus 65. It's a 45% reduction. Displacement, 99 millimeters, which is 8% reduction. Not massive. But if you consider that for every single kilogram that they are saving in an aircraft, they are saving thousands of liters of fuel. I mean, in fact, they work actually more in tonnage, if I remember correctly. But now they are saving lots and lots and lots of fuel per year. And now, again, every bit of fuel saved is also less environmental impact. It also costs the company less, which means they could either A, fly more economically, or B, they could fly with more. Also, when I was talking over here about the actual loads that's been applied, if you take a look over here, you'll notice we don't have that same cherry red. We've got more of the orange, and it fades a lot slower over the entire partition range. You notice it goes, all the yellow goes all the way to the sides, and then also it's distributed far further. We've only got no loading right at the corners and the edges over here. So it distributes it far better over the area. Now, you'll notice it's got this actually very strange zigzag design that's all over there. Now, when they were actually working with this, what they did is they fed it two primary algorithms, which was slime mold, I know it sounds very strange, and mammal bones. Now, the reason for it is because slime mold makes very efficient bonds and it's very efficient with its rooting, and mammal bones because it's very strong for its size and its mass. It's amazing, actually. Our bones are an amazing marvel of a biological achievement if you actually take a look at them. So they combined this together, and through generative design, they actually came up with this design, which at first looks very strange and disorganized, but the proof is in the pudding. If you'd actually look over here, or should I say the proof is in the simulation. You can actually see how much this reduced it by. Well, reduced the load and increased the strand. Now, one of my favorite ones was the JPL lander. By the way, JPL, Jet Propulsion Laboratory, is basically part of NASA, so the guys who are putting stuff into space. Now, big thing over here again, when you're sending objects to space, every kg saved means you're saving tons of fuel, because it's not like a 1-for-1 ratio. To put anything in space takes lots of fuel and big rockets. So in this, they would have been happy with like a 10% weight reduction. They received a 30 to 35% weight reduction. So in this, weight is key. Weight is king. And of course, it still has to be strong enough to do its job, but now it's strong enough and it's even lighter. So looking at this, it's just amazing to see how far we have come and what we can achieve using our generative design capabilities. Yeah, it was fascinating to actually see this. So now we get on to the more interesting part about how is this done actually in Fusion 360? And as I say, with great difficulty, not really. It's actually a lot easier than people think. So how is this done? Well, let's skip over to Fusion 360, and I'm actually going to be doing a little bracket very similar to this one, though mine doesn't look as interesting if you ask me in some of these cases as what these do. But yeah, let's get to it. Going to quickly jump over now to our Fusion 360. And this is our environment. So at the moment, if you take a look over here, I've got my brackets open. And I've, for one, have got the wall and shelf already defined as a part. You could have a massive wall and a shelf, but just be aware that if you're going to do something like that, it's going to make it take a lot longer to solve. This one already has taken ages to solve, and I'll actually take a look and show you guys the solution, well, some of the solutions in a bit. But do yourself a favor, keep it simple. So in this, I've just made a simple, okay, that's my wall and shelf. I've got a lower bracket, and I've got an upper bracket, and then I've got my holes. Now you may be wondering, why do I have this weird crosshash pattern over here? But that's because, think about it, when you're putting screws or something in, I don't know if you've ever assembled anything, and they've put the hole in, but then they've got something obstructing the hole. And now to try and get a screwdriver or something in there, you have to get like one of those little mini things to try and get in there, and then your hand can't get in, and it's difficult to try and get in. So in this case, what we've done, and I'll explain to you in a sec, is that we've told it that this is going to be kind of a safe area. We don't want to build anything in there. Cool. So I've defined basically my geometry. Now, okay, cool, I've defined this geometry, but now what do I do with this geometry? Simply, we need to use our drop-down on design and go to generative design. And you can see, whoops, I've jumped to my generative design and it's got a whole bunch of stuff I don't know of. Now, it's actually very simple if you think about it this way. I'm going to show you some basics of how to get you up and running. So firstly, we want to take a look, and I like to start on my left and then work to my right. So Firstly, let's take a look at things. We do know what we need to do. We do know what we need to have and avoid. So what I'm going to do in this case, I'm going to go and I'm going to say, okay, cool, over here, edit my, well, preserve my geometry. So what this is going to do is it's going to say, okay, I want these specific items to be in here. So think about it this way. If you've got like a place like where a bearing's supposed to be, like a housing, and it can't be any smaller than that, or that's actually a poor example, but if you've got something that you want to preserve, this is what you'd use. Select those two and select OK. So what we are saying is, okay, at the end of the day, it has to have this minimum geometry in there. It can be expanded a bit over it, or it can be around it a bit, but it can't be any less than that. So we're saying that is what we need. Then what we are saying is, okay, what is the obstacle geometry? So in this basically being that it can't go past there, and also we don't want it to get in the way of our holes because we want to be nice people. When we want to design things, we want to design it in a way that it can be easily put together. We don't want people swearing at us and saying, these people don't understand how things go together. Oh, they're making my life difficult. I want to make people's lives easier. I'm going to go, okay. So now, as you can see, I have got this nice red and green. So all we've basically just told this thing is keep this green geometry and respect that you cannot interfere with the red geometry. Nice. Now that we've got this done, we can start working around this a bit more. So firstly, like if you've ever done any simulation stuff, you know that we have to kind of start putting some forces and a little bit of things in, but don't worry, this is not a complex thing. Anybody can actually do it if they have a basic understanding. Firstly, this little yellow arrow that's pointing down, that's force of gravity. Don't worry about it too much at this stage. For this type of demonstration, we're not going to worry about it as much because it's going to be a very small part of actually what we're doing. So what I'm going to do here is I'm just going to click the on the preserve geometry, and I'm just going to hide my obstacle geometry because what I'm going to be doing here, it's just going to be getting in the way. But don't worry about hiding it. It's not going to impact our studies at all. So what I'm going to do is I'm going to come here at the back, and now the next section on my design conditions, I'm going to put a structural constraint. I'm just going to click here at the back. So it's going to put a fixed constraint on the back here so that it can't move. So this is like if you bolted it onto a wall. And click OK. Nice. That's all we needed to do. You can see the little lock. Now what I'm going to do is I'm going to give this thing some loading, because think about it, a shelf normally has stuff on it. So I'm going to go structural loads, and I'm going to click the top. Now it's going to ask me, okay, cool, so how many newtons of force it's going to go on this? Well, depends. How much do you want to put on there? What do you want to hold? In this case, I'm just going to say, okay, 500 newtons. Okay, 500 newtons of force pushing straight down. Cool. So as you can see, all those little arrows combined into one, but that's basically 500 newtons across the entire face pushing down. Now, you could use this, but also, oh, I did almost forget one little thing here. Nope, I didn't. Aha, sorry, I forgot to set it on. Okay, so firstly, we're going to take a look at this and we're going to say, okay, 500 newtons of force pushing down. But now, that's not very realistic, because think about it. How often do you walk into a shelf, bump a shelf, push up on a shelf, do something like that? So we want to add like a little bit of robustness in in basically your other directions as well. So firstly, let's going to right click on my load case and say clone. Just makes our lives faster because then we don't have to reset up. The reason why I opened it there is I want to show you this. See my gravity, force, and my constraints. I don't have to set all that up again, just makes our lives faster. So in our load case, what I'm going to do here is I'm going to say, okay, loads, expand it, and go to my force, and then I'm going to edit my structural load. And all I'm going to do here is I'm going to flip my direction around. You notice the arrows are pointing up. And I'm going to change the load to like half the load. I mean, if you wanted to, you could calculate things like what is the maximum that somebody's going to hit their head on it and force the shelf up by, but that's up to you. At this stage, I'm just playing with numbers. I'm just going to put 250 newtons of force and go okay. Cool. Now we've got a force pushing down. We've got a force pushing up. Well, what about the sides? Because somebody might hit the side of it, or something may rockets. You may have an earthquake. You never know. So in this case, I'm going to just quickly collapse my load cases again. I'm going to clone the second one, and I'm going to go back to my loads. I'm going to edit my structural load. I'm going to say, okay. I'm going to change my vector, and I'm going to set that as 0, and then my x direction. So x direction. If you take a look, if you get confused with this, by the way, take a look at your view cube. It will tell you also as to where your directions are, or give you a bit of an idea at the very least. I'm going to say 250 newtons in my x direction, positive. Okay. Oops, no, there we go. I'm going to clone my load case again. And I'm going to get to my forces. So you notice, by the way, if I go to my force on my load 3, I just click on it, you can see the little arrow pointing that way. If I go to force 4, you can see it's still pointing in the same direction. All I have to do is go edit the structural load, and I'm just going to put a negative. Okay. So it means that force is in the one direction, another force is in the other direction. Cool. Now basically I'm happy with my forces because now I have got one pushing down, one pushing up, one pushing to the left, one pushing to the right. And then I've also got it fixed to a wall. Now once this is basically done, this is pretty cool because now I can actually start checking things. Firstly, we want to give it some objectives. So what our objectives is basically doing is how do we want this thing to work? So are we going to go for minimum mass or maximize the stiffness of it? So, you know, what is our design criteria? What are we more worried about? And then also our safety limits. Just for this exercise, I'm just going to set it to 1. I would not recommend setting it to 1. And basically the safety factor is how many, how basically is it multiplied the loading by in order to make it safe. I highly suggest if you don't understand this, go read up about it. It's a very good idea to look it up. But in the simplest terms, it's basically a multiplication on the actual loads. Okay, modular frequency. If it's going to be maybe moving around, so if you've got something that's continuously in motion, moving around, you can tick that and you can say basically what is it rotating around by, what is it oscillating by, etc. And in this case, you can see 20 Hertz. I'm not going to use that because it's going to be a bracket. Unless it's in an earthquake zone, I don't know. And then also, what is the maximum minimum displacement, or the displacement you're looking for? For this, just for the sake of making our lives easier, I'm just going to leave it on minimize mass and safety factor of 1. Because also this is going to give us a very interesting result that you'll see a little bit later. Okay. You can also do your manufacturing. So if you click manufacturing, you can say, okay, so what production volume are you looking at? So how many of these you're planning to do? Because it's going to directly affect what you're busy, well, you know, how you're going to make it, how many you're going to make. Unrestricted means basically, are you going to do you want it to give you an unrestricted by actual manufacturing methods? That's what it's asking you. The additive, which will be additive manufacturing. Additive manufacturing being your SLS, so selective laser sintering, SLM, selective laser melting, if I remember correctly, and your filament deposits, so FDM, if I remember correctly. So those are your different additive manufacturers. There are more. I mean, there's resin, so there's so many other ones that you can go in. What you can also do then is specify your milling, etc. 3-axis, you can drop it down to be multi-axis. and then quite a lot of other things over here. We could spend quite a while just going through the manufacturing options. But for this case, I'm just going to leave it as default. And yeah, we'll take it from there. I'm going to go OK and accept the defaults. So I'm basically going to be given an option for, when you'll see when I generate, I'll be given an option for unrestricted, additive, and milling. Next, materials, because we have to know what materials, how we're going to, what is it going to be? Because think about it, if it's going to be running a generative design, it has to know what it's made out of, or else it's not going to be able to satisfy our loading conditions that we've given it, or our forces. So if we open the study materials, we can say, oh, okay, I want to then, I'm going to drag aluminium, into my material. So it's going to calculate for aluminium. Now, just an important thing to note, and there's something that I kind of didn't do right on my one, which I'll show you now, is that I didn't select the materials with the cost estimation. So what it is basically been going through them and adding cost estimation to these, which is driven by another site, but I'll get to that in a sec. So I'll go cost estimation, aluminium, and then I could go here and I can actually grab multiple different items here. And let's say stainless. I'm just going to select those two. You could even go and select anything you want on here. By the way, if it doesn't have the cost estimation, it just simply won't give you an estimated cost. It will still work perfectly fine, though it may give you, it does give you a warning. So I'll actually put one on here so that it does give me the warning. Let's see. Let's go nylon. So you notice the nylon one doesn't have the little calculator on it. And I'm going to go close. You'll notice I've now got a warning there. And if I click my pre-check with my warning, it says, warning, the material nylon is not supported by the cost estimation for the methods, unrestricted and additive. Consider changing the manufacturing methods or material. So basically it's complaining because I picked one that doesn't have that. Now, an important thing that people love to skip out or they get confused with it is this first section over here, which is kind of a simulation of the generation. Now, when I click on it, this may take a few minutes depending on your hardware, but what it's going to do is it's going to do a quick generation of basically what you're looking at. It's not the complete generation, it's just more like of a preview. And the reason why you want to do this preview, and it's always a very good idea, is that remember those holes that I had in, the obstacle? Sometimes you forget to put those in. I mean, we're all human, we make mistakes. So in this case, you're showing the holes and you're saying, hey, look, okay, I can see this, I can see that it's being formed, and I can see that it is, I've got that place. Or otherwise you can say, oh no, I forgot something, I need to put it in. So before we are spending credits, which I'll talk about in a second, we can make our lives faster, easier, better without having to mess around. Because also this generation does take time, I'm afraid. Okay, so now that we've taken a look, and if also this is at low. If you want to change the preview level, you can also change it to medium and high. But like with rendering, I'm afraid the higher detail you go, the longer it is going to take. Okay, when you're happy with it though, you can click the generate button. It's going to ask me to stop the viewer. I'm going to say yes in this case. If you see a status with a warning, you can then go repair, and then you can try and repair the warning. So what I could do here is I could go back into my materials, right-click on the material and just go delete, and you can see my pre-check is now fine. So now when I go generate, it says it's ready to generate. Like I said, if you did not have that, should it be fine? Now, one thing that I have in mind, because of being a reseller, etc., and that with it, is that what this would do is it would normally cost you cloud credits. It used to cost 25 cloud credits to generate the study, and then it costs 100 cloud credits in order to actually use that specific version in the study, which I'll go to in a little bit. Now, this may sound like a lot, but the thing is, it's firstly, you're leveraging the power of the cloud, and you're getting hundreds of options depending on how you set it up. And then also what you're getting at the end of the day is a usable part with everything predefined, all the loads, everything done already on it. You could basically take that, give it to a manufacturer, and they could make it for you directly, which eliminates time, uncertainty, everything from the equation. So normally what we'd do is we'd hit generate the study. Now, I've actually already done this, so I'm not going to hit generate study now because this takes a while to do. I'm going to go close, but this would normally generate our study, and it would hop us into a menu like this. There we go, magical transition. We're done. So what this does eventually is it creeps up and it displays our various iterations. And as you can see over here, I have got aluminium. And you can see, oh, okay, this one did actually. So this one actually has calculated. Oh, there we go. You can see this one over here hasn't calculated the cost. Because it's glass, it doesn't know what the costing of the glass is. Yes, I made one with glass. So these are all of our iterations. And you can see I've made it out of aluminium, ABS plastic, glass, and you can see all of these different ones. And some of them you probably wouldn't have. Some of them are still actually generating, because I actually switched it on this morning because I was wanting to play around with the model. But some of them are pretty interesting. So just a bit of information how this actually works, by the way, is it will take it actually takes the original shape. So let me actually go into one of these. I'm just waiting for it to finish our view. It's thinking, it's thinking. There we go, now it's finished thinking. So basically what it does is it starts off with your iterations. So this would be your first iteration. We're just waiting for it to generate. Now it starts off with a nice big block around the object that you're looking at. And then what it does is it goes, okay, let's analyze this with the stresses that was given. And what we'll do is we'll take, okay, whatever is stressed we'll keep, whatever is not, we'll get rid of it. We'll chip it away a little bit. So through a factor of subtraction that it actually does, it slowly goes through it. And as we're waiting for it to generate, basically it slowly goes through it and it gets rid of any information or any parts that is not necessary, because all it's going to do is it's going to add weight without actually adding any, if all, structural integrity to it. And as you can see, if we jump to iteration 6, just waiting for it to generate here, you can see it's gone quite far through here. And then at our final iteration, come on. Ah, goodness. There we go. Our final iteration, we've got this very interesting looking component. And that is basically how the generative design, how it's actually working in the background and what it's looking at. You can also change your display to see how the stress is going to be, where the stress is going to be, and then also previews, etc. You can also see our preserved geometries, both of our preserved and also our obstacle geometry. And then what we can also do is then compare this with others, which I'll show you in a second. You can then get the design from the outcome or otherwise populate it to a mesh. Just one thing I wanted to show you here before I close this is that you can actually see here on the right all of the properties actually of it. If you actually was paying attention in the previous window, you would have seen all this information there. What was quite interesting is that it basically, firstly, this is a converged model, so it's everything put together. And it's an unrestricted manufacturing method, excuse me. Now, what this means is basically that it's not taking into effect of how it's made, so whether it be additive, subtractive, or hybrid between them. It is just saying, based on what you've given it, this is the best model considering the information you've put in. Then also here you can actually see how much it would cost maybe to make. the cost of it, the volume, the mass of it, 1.2 kgs, and then also what what safety limit is actually at the moment. So minimum safety factor I set was 1, and it adhered to 1 of all things. Maximum displacement in millimeters, 0.16. So it's actually pretty cool. Oh, and a priori, I really hope I pronounced it correctly, is the place that actually now drives that. So that's pretty cool. But now, let's say we wanted to compare several different types. So firstly, I just wanted to jump to, let's say, if we open this one. Now, over here, the reason why I'm jumping to this is because I wanted to show that this is the same model that is now generated with an additive manufacturing method, and it was orientated to the Y. So in other words, orientation Y. There we go. So we'll be printing with the bed at the bottom, and it's orientated to the Y. So what does this mean? It just is that when it's actually making this, it will be easier for the printer to actually create it. I must admit, that is a very strange looking design. But basically, that is what its solution would be to this. I'm going to go finish outcome. Excuse me. Okay, so with this, we have got our various models. And what we can do also then is see, okay, let's then take a look at something like, where is our, I'm looking for one that is actually a machine one. 3-axis milling. Oh, that's not a very nice looking one. As you can see, it does generate quite a few options, so sometimes finding the one that you want can be quite interesting. Unrestricted, additive, additive. Ooh, lots and lots of different ones that we've got here. Okay, I'm just going to jump to one of these. It's not going to be the nicest of all looking ones, but it will give you an idea, because basically what it's doing is it says orientation is in the Z direction, and its manufacturing method is in the Z direction. Sure, I can't really even see that. My apologies. But if you look carefully, basically what it's showing here, let's actually put that there. Oops, okay, that was a bit of a fail. Yeah. So this is part of the reason why you would want to have multiple iterations of this. It's just because of the information that I put in there, and it didn't really like that. But yes. So with this being said, what we can do is if we want to see multiple of these, what we can do is we can select multiple ones. Let's say this one, and I think that one also looks quite interesting. Actually, let's go for that one. Multiple selection, compare. So just waiting for it to get it together. As you can see, it does take a little while. This is dependent on both the hardware of your system and also your internet connection at the time. So what it will eventually do basically is it will give me several different views, and those several different views are going to be each one of these mole iterations. So it will be of the first one that it gave me, the first solution, the second solution, the third solution, etc. There we go. And yeah, it's generating. I was waiting for the other two to come down. Switch this all to model view. And as we're looking through it, we can then actually see the different iterations. As you can see, these ones are pretty similar. Yeah, you can then see what they're going for. And that was comparing those 3 different file types. Cool. So in a nutshell, that's what it is. By the way, what you could also do if you wanted to, this was just one of the views, which is the properties view. We've also got thumbnail views, where you can then see just the thumbnails of the objects that you want to see. You could also do a scatter plot. So what the scatter plot will do, which is quite interesting, is that it will show you the criteria. So in other words, this one over here, we can see gives us our maximums. So weight versus strength, or safety factor in this case, sorry. Or we can say mass in kgs versus, maybe let's say volume. And go to one of these. Scales a little bit out. But if we hover over it, you can actually see these ones that are being generated. And this gives us an interesting information. So this actually just helps us visualize what is going on here. You can also sort it by using the different sorting on these sections. Or otherwise, go to the table view, and then you can see it in a nice table view. Cool. So now, once it's been actually worked on, and you've selected the one you want, you can then take it into your system and to use as you wish. I'm just going to select this one, wait for it to generate, and I'm going to export it. Create design from this outcome, show cloud credit costs and balances. Like I want, so cloud credits. So this is going to cost me 100 cloud credits to download. Okay, cool. Now just remember, like I said, this would be a ready-made part ready to go. So the 100 cloud credits could possibly be very, very worth it. I'm going to click go, create design, and then it will actually create it on this. So it's busy actually solving, and then what I'll get at the end of the day is I will get a model ready to go. Okay guys, I'm going to stop it over here because basically from here on out it would be the same as just using normal Fusion in a formal environment. So firstly, my outro, my observations. My observations of what these generative design is going to be about is that it's going to be the future of our design because it helps us. And also, it's not a case of that what people may think that, oh no, it's going to take my jobs, it's going to do with us. It's like computers or CAD when it first came out. It's there to supplement us and make us better, faster. It's there to take what we can do and just push it beyond what we can currently do. So at the end of the day, it's an amazing tool and we can actually produce things beyond our wildest dreams while making things lighter and stronger. And it just, your imagination sometimes only is one of your greatest limits. And in this, it just helps augment it. So thank you very much. Thank you for joining me on this. Do I have any questions from anyone? Okay, if you've got any questions, just put it into the chat. Okay, it seems to be very quiet. I'm just going to wait a minute or two. Okay, well, basically, guys, if there is any more questions or anything, please don't hesitate to get in contact with us. So you can get hold of us at any one of our branches around the country, either giving us a call or dropping us an email. And just to reiterate, I'm Quinn Kennedy, application engineer, part-time trying to take over the world. Thank you very much for joining me. Hope you have a wonderful day. Cheers, eh? Bye.